This video will cover the DFS algorithm and interesting properties of it. DFS is a shortcut for depth-first search. This is one of the core graph algorithms, and it is used to solve other important graph problems. Let's start with an example to gain some intuitions. Later on, we'll dive into more details. DFS algorithm searches a graph until it scanned all of its vertices. As the name implies, the scanning mechanism is to go deeper whenever possible. Here we start from a random vertex, move to one of its neighbors, and as long as there is a new vertex to discover from the current vertex, we continue. When we reach the vertex that can discover any new vertex, DFS backtracks in the same path until it can discover a new vertex. Here it had to backtrack only one step, and then it could discover another vertex. Here we had to backtrack to the starting vertex and start a new path. When there are no more vertices to discover from the starting vertex, we'll start from a new undiscovered vertex, until all vertices are discovered. We'll see in much more details how it works soon. We'll also see that looking at the edges the DFS used to discover vertices form a forest of trees, where here we have two. Let's see pseudocode of the algorithm. The input for DFS is a graph G, which can be either directed or undirected. We assume it is given as a adjacency list. Please refer to a link in the description if you'd like to learn about adjacency list representations. DFS will track the following properties: the parent of each vertex, which is the vertex who discovered that vertex during DFS Run, the time in which each vertex was discovered, and the time in which DFS finished handling a vertex. Lastly, DFS also assigns color to vertices, such that white means that the vertex was not yet discovered, yellow means that the vertex was discovered, and black means that DFS has finished handling that vertex. DFS starts with initialization. For each vertex v, we assign the color white, mark the parent as null, and set discovery and finish time with 0. We also init a global time variable with 0. We then go over the vertices in a for loop, and for each vertex v, we check if its color is white, meaning v was not yet discovered. If so, we visit vertex v, which means we start a search from that vertex. Let's see the visit method. First we assign the color yellow to mark vertex v as discovered or visited. We increase the time by 1 and set the discovery time of vertex v to that time. We then loop over the neighbors of v by looking at its adjacency list. For each neighbor u, we check if it was not yet discovered. If so, we mark its parent to be vertex v and continue the search from that neighbor u by recursively calling visit on u. This part shows that DFS search deeper when possible. Later on we'll see a complete running example, so the recursion will be much more clear. When we finish going over the neighbors of v, we increase the time again, and set the finish time of v. We see the meaning of the finish time now, that it is set after we've finished the search from v, and discovered all possible vertices from v. We also color v as black to mark it as finished. Near the end of this video, we'll also see a non-recursive version of DFS. Before moving on to an example, let's talk about the time and space complexity. Here we have the DFS pseudocode we just saw. So what is the time complexity? First there is the initialization, which has a for loop on the vertices, and all other operations are of constant time. So it takes big O of the number of vertices v. Next we have another loop over the vertices, where we call the visit method and the visit method itself. Inside the visit method we do operations of constant time, such as coloring the input vertex v and setting the time, and we also have a loop on the neighbors of the input vertex. So, without including the time complexity that is resulted from the visit calls on the neighbors, we have on each visit a time complexity of big O of 1 plus big O of the number of neighbors. But how much it costs when including the visit calls on the neighbors? To understand it, the key idea is to think about it aggregatively and ask, how many times visit is called for each vertex? The answer is exactly once, thanks to checking if the vertex is white before doing so. So in total we get big O of v plus e, by aggregating the visit time complexity for all vertices. What about the space complexity? All of the operations are of constant space, except the fact that we use recursion, which makes the call stack grow. The worst case scenario is if we start from a vertex that discovers all vertices at once, without a need to backtrack at all. If it happens, then the call stacks hold the visit method states for all vertices at some point. So the space complexity is big O of the number of vertices v. Let's move on to see an extensive DFS Run example to ensure the algorithm is understood. On the left we have the algorithm, and on the right we have a directed graph with 9 vertices we are going to use for this example. We name the vertices with letters arbitrarily. We start with the initialization loop, setting for each vertex that there is a null parent, 0 discovery time and 0 finish time, to mark it was not discovered and not finished. We also define a global time counter, starting with 0. Here on the bottom right, we'll monitor the call stack. We then start the search loop, choosing a vertex arbitrarily. In our case, let's say it is vertex y. We check its color and see it is still white, meaning it was not yet discovered, so we visit it. We write y in the call stack to specify the context of the method. Of course that in reality, the call stack contains other information that helps to manage the program execution. Here we just write y for context. Inside the visit method, we first color as yellow the visited vertex, which is y. We then increment the time and set the discovery time of y to be 1. We then go over the neighbors of y. Y has only one neighbor, which is z. We see z is still white, so we mark y as its parent and visit z. We add z to the call stack and clear the local state. Now we run visit on z, so first we color it as yellow. We then increment the time and set its discovery time to be 2. We then go over its neighbors. Z has 2 neighbors and we randomly start with vertex n. We check and see n is still white, so we set z as its parent and visit n. We update the call stack, clean the local state and go to visit n. We color n as yellow to mark it is discovered. We increment the time and set its discovery time to 3. We then should go over the neighbors of n, but we see n has no neighbors, so we skip the for loop and go to increment the time. We then finished handling n, so we set the finish time with 4 and color it as black to mark it is finished. We ended the visit method for n, so we go back to where it was called from, removing n context from the call stack and setting the local variables of v and u to their state from before calling visit on n. We are back to handling z, and we move on to the next neighbor of z, which is q. Q is still white, so we set its parent to be z and visit q. We add q context to the call stack, clean the local variables and go to visit q. We color q as yellow, increment the time to 5, and set 5 as the discovery time of q. We then go over q neighbors, starting with x. X is still white, so we set its parent to q and visit it. We update the call stack and local state and start to visit x. We set x color to yellow, increment the time to 6, and set 6 to be the discovery time of x. We then need to go over the neighbors of x, but it doesn't have any neighbors, so we skip the for loop. We increment the time again and set the finish time of x to be 7. We also color x in black to mark it as finished. We clean the call stack context for x and restore the state from before calling visit on x. We are back to handling q, and we move on to its next neighbor, which is m. M is still white, so we set its parent to be q. We update the call stack and local state and go to visit m. We color m as yellow, increment the time to 8, and set the discovery time of m to be 8. We then see there are no neighbors for m, so we skip the for loop. We increment the time to 9 and update the finish time of m to be 9. We also color it as black to mark it as finished. By that we ended the visit method of m, so we restore the call stack and state and go back to where it was called. We are back to handling q, and we already handled all neighbors of q, so we exit the for loop, increment the time to 10, and update the finish time of q to be 10. We also color it as black to mark it as finished. We ended the visit for q, so we clean the call stack context and local state and go back to where it was called. We are back to z, and we already handled all of its neighbors, so we exit the for loop. We increment the time to 11 and set 11 to be the finish time of z. We color z as black as we finished handling it. We clean the call stack and state and go back to where it was called. We are back to handling y. We already iterated on all the neighbors of y, so we exit the for loop. We increment the time to 12 and update the finish time of y to be 12. We finished handling y, so we color it as black, clean the call stack and local state and go back to where it was called. Y was our starting vertex and we've ended the search from it. We then need to continue the search from another starting vertex, so we go to the for loop and encounter the vertex t. Note that if we would encounter a vertex that was already handled, we will just skip it thanks to the check if its color is still white. T is still white, so we visit t. We set its color to be yellow to mark it was discovered. We increment the time to 13 and update the discovery time of t to be 13. We then go over its neighbors. It has only one neighbor, which is s. S is still white, so we set its parent to be t and go to visit s. We update the call stack and state and visit s. We color s as yellow. We increment the time and update the discovery time to 14. We then go over the neighbors of s. Say we start with q. Q is not white, so we choose another neighbor. There is only one left, r. R is still white, so we set its parent to be s and visit r. We update the call stack context and local state and go to visit r. We color r as yellow, then we increment the time to 15 and update 15 to be the discovery time of r. R has only one neighbor, which is y. Y is not white, so we go back to the for loop and exit since there are no more neighbors. We increment the time and update the finish time of r to be 16. We also color it as black, since we finished handling it. We clean r context from the call stack and go back to where it was called and restore the local state. We are back to s and we've checked all of its neighbors, so we exit the for loop. We increment the time and set the finish time of s to be 17. We then color it as black. We clean the call stack from s context and go back to where it was called, restoring the local state. We are back to handling t, which has no more neighbors to check, so we exit the for loop. we increment the time to 18 and update the finish time of t to 18. We color it as black to mark it as finished. We clean the state and go back to where it was called. All vertices were discovered, so any other vertex that will come up in the for loop here will not be visited again, so we end the example here. Next we discussed few interesting properties of DFS. We have here the result of the DFS run we just saw. The first property we are going to talk about is that the predecessor graph, GP, is a forest. What is the predecessor graph? It is a graph that is composed of the same vertices as the original graph, but only with edges used for discovery. It can be generated from the DFS result using the parent property we have on each vertex. In the example here, we have a tree that starts with y, since its parent is null. Z is in the tree since y is marked as its parent. Then n and q are added since z is their parent. And similarly we add x and m. Next we have another tree that starts with t. We see we have a forest that is composed of two trees. Now let's talk about the parenthesis property of DFS. This property means that if we treat the discovery times as open parentheses and the finish time as closing parentheses, then we get a legal parenthesis structure. For example here, we write all timestamps, and below we write open or closing parentheses based on if this timestamp was used for discovering a vertex or for finish handling a vertex. 1 was used to discover y, 2 was used to discover z, 3 was used to discover n, so we start with 3 opening parentheses. 4 was used to finish n, so we have a closing parenthesis here. And it goes on similarly. We give each pair a different color so it will be easier to see. Notice that we get a legal structure. Another interesting property of DFS is that the search can be used to classify edges into groups. Groups, we'll see, have important role in other graph tasks. On the left we have the DFS run result again. First type is tree edges. Edge uv is a tree edge if u is the parent of v. For example, on the example run on the left, one tree edge is yz because y discovered z. Another one is sr because s discovered r. Second type is back edges. Edge uv is a back edge if v is an ancestor of u. There are no such edges on the example on the left, but say there was an edge from m to z. Then it was a back edge because z is an ancestor of m in the search, meaning the edge go in the backward direction to the search direction. The third type is forward edges. Edge uv is a forward edge if v is a descendant of u. Here also we don't have an example in the original graph, but say there was an edge between z to m. Then it is a forward edge because m is a descendant of z. We see this edge goes forward in the search direction. Lastly we have cross edges, which are all other edges. We can also say that edge uv is a cross edge if uv are not related, meaning none is an ancestor of the other. In the example, a cross edge for example is between S to Q, as they are not related. It is also interesting to note that it is a cross edge because the edge crosses between the two trees on the predecessor graph. But not only edges that cross between DFS trees can be cross. For example, if there was an edge between Q to N, it was a cross edge, as they are not related. Let's move on to see a non-recursive version of DFS. The beginning is exactly the same as before. We are only going to change the visit method. We will also track the same properties we tracked before. Let's go over the non-recursive version of the visit method. First we init a stack and push v to the stack. We then have a while loop that will run as long as the stack is not empty. In the while loop, we pop a vertex from the stack and store it in a variable u. If u is still white, we discover it. We color it as yellow, we increment the time by 1 and set its discovery time. Then, for each neighbor of u, if it is still white, it is the first time we see it. So we update its parent to be u, and we push it to the stack. After iterating over the neighbors, we push u to the stack again. The next time we will pop u will be after we popped all of the neighbors it discovered and all of the vertices discovered by its neighbors and so on. So, when we will pop it out next time, we will be able to mark it as finished. So, if the vertex we popped out was not white, then this is the second time we pop it from the stack, and we already finished handling it and the vertices it discovered. We set the color to black to mark it as such. We increment the time by 1 and update the finish time. And that's it. Note that the use of the stack here is intuitive as it replaced the role of the call stack in the recursive version. Okay, we learned a lot about DFS in this video. Where can we go from here? DFS has many important applications, which we didn't cover here. Some examples are finding a topological sort of a graph, find strongly connected components of a graph, or check if a graph has a cycle. Stay tuned for dedicated videos about these topics in this channel to learn more. Thank you for watching. If you like this video, please don't forget to hit the like button and subscribe to the channel.